Now, going back to, in order to study torsion, because look, if I grab the two end of this bar, miss it. I'm not imposing any axial load, right? It's purely shear. So in order to understand torsion, I need to understand shear. And all we studied so far is most like normal stress. So I have to first talk about shear. Now, everything is exactly simple. The analogy is so strong that some books even don't consider separately. They just talk about this and then they apply it to shear. Now, how can we do that? Now, instead of doing something like that, you consider an element as you apply, let's say this element fixed to the ground, and you apply the force F like that, the shear force. You see, this is not normal, shear. The normal force is this way. See that? It's perfectly shear. Now, the moment you apply that force, you're going to get some deformation. So you have something like this. Then you have an angle gamma. What do I get when there is no force here? What is the value of gamma? 0. And then I can say that when I increase F, gamma also increases. Now if you go to lab and make some specimen similar to that and put it in the machine and apply force and measure gamma, exactly what we did here. Here, what did we measure? We measured axial load and the strain. And we made a plot like that. Now, if I measure gamma and force and draw it, I'm going to get exactly something like that. But what is this axis? Gamma. And this axis? Shear. Now, it's not sigma. See here was sigma. Normal stress. This is perfectly shear. The normal is this way. Because I have 0 component in normal, so I have 0 normal stress. It's perfectly shear stress. Now again, I have these 3 points showing up. Here, ultimate shear stress and failure. After that, the stress breaks. Okay? Now, what can I say about the This curve has a slope here. The slope, let us call this a slope G. We call this a slope E. Long modular of elasticity. Now this slope is also a modular of elasticity. We call it shear modular of elasticity. And in the lab, because we didn't cover that, some students have like co-requisite. In the same time, they have that and they have mechanics of material. They did not use shear modular of elasticity from the table. They thought that, well, modular of elasticity is E. But there is something else, shear modular of elasticity. They are not equal. This slope is not equal to that. Why? Because the nature of the test is different. That's perfectly shear, that's perfectly normal. Right? But let me tell you something. This G is available. This is like known. We don't compute that. This is known. How do you get that? With the check mark here. You go to the tables. Whatever material you have the long modular of elasticity, shear modular of elasticity. You can also find these 3 points if you are interested. Okay? So, now this relation, what can I write about the relation here in this region? Is equal to the slope G times the variable of linearity. What's the x-axis? Gamma. This is also called Hooke's law. Hooke's law for shear stress. There you go. As you can see, the dimension of shear stress, what's the dimension of shear stress? Well, shear stress is a stress. And what's the dimension of the stress? Force divided by area, right? What's the dimension of gamma? Well, dimension of gamma is an angle. It doesn't have any physical dimension, right? It doesn't have like meter second, no dimension. So therefore, the dimension of G is also equal to the dimension of the stress. So this is exactly like modulo per assisted E. You see it was in gigapascal, 200 gigapascal, that people like this thing. G is also in Pascal. Pascal because this doesn't have any dimension. It's dimensionless. Okay? So now we need to use this relation. So in this relation says, if you find the angle of deformation and multiply that by shear constant, then you get shear stress. Now we are going to use that in order to do torsion analysis. So let's first consider a symmetric cross section. And here comes torsion. So let's say this is stationary related to the wall. And let's say you apply the torque P. See, this is, you don't have normal stress. You have perfectly torque shear that causes thing to rotate. Okay? Now, what I can say about this particular cross section, I can say, well, you remember what we did in bending? We tried to find a neutral axis, that the bending stress was 0. And then I wrote the bending moment with respect to that, the axis passing through that center. And the y was 0 there, and therefore sigma was 0. Okay? And then I did the rest of the derivation. Well, we are going to do exactly the same thing here. And we are going to say that the shear distribution is equal to, let's consider this point, say polar coordinate. You guys have polar coordinate factors, but you all have polar coordinate. So what is polar coordinate? The Cartesian one, instead of saying xy, xyz, right? In polar, you have r theta, the distance from the center and the angle from the x-axis. Again, you have two variables, xy, r theta. So in this case, unlike the bending, in bending we use Cartesian, right? In this case, let's use polar. So let's consider an element here. There you go. That is located, this element is located distance r from the center. Okay? So in this case, I'm saying the stress at any location r is equal to a constant times radius. This is like conjecture. So I'm just assuming the stress distribution is a constant times r. What is the main assumption of this distribution? Existence of neutral axis. Why? Because when you put r0, what do we get? the shear stress is 0. And then later you can show, I do it as an assignment, that you can prove that the neutral axis passes through the center. Again, with this kind of shear, exactly like bending on it, right? So we have a neutral axis that is passing through there, and then we have a distribution like that. Well, do I know the constant? Do I know the constant? I do not have the constant, right? I just say constant times radius. I do not have it. What information do I have? The first information is tau, the shear at R is equal to 0 is equal to what? 0. The shear at neutral axis is 0. That's the definition of neutral line. The shear at R is equal to R. Let's say the radius R. The shear at R is equal to tau max. Still I don't have it. Well, I know that the shear, because it's a linear relation, the maximum possible happens at the edge. Right? So I can, if I place here, I can say that tau at any distance R is equal to tau max times R. Do you agree? That's exactly, I evaluated this equation with this condition. So put here, put tau R is equal to R is equal to constant times R is equal to tau max. Then the constant is equal to, you actually do the R here. Then the constant is equal to, so here we put constant times R is equal to here. Constant times R is equal to tau max. Then constant is equal to tau max over R. Put it there, back to this relation. Then you get tau is equal to, the constant is equal to tau max over R times R. That's what you have. You agree? That's exactly based on the assumption. You remember in the bending, we have, this is a bending moment. Like that. And then we had a y here. Distance from the neutral axis. So you said sigma is equal to proportional times y. But we have positive, negative for during many moments, right? This exactly analogous to that what's in oral movement. Right? So I have this relation. So far I have this relation. Now, you may ask, so what is my maximum? Tau max. What is my maximum shear? Right? So how can I find my maximum shear? Even, you see you have T, the torque that is applied to the entire cross section. And you want to find tau max. How can you do that? Yeah.
Solve at the largest radius.
So put largest radius here. Okay. Put R is equal to capital R. Then what happens? Tau becomes tau max. Do I get new information? So the question, how can I find that tau max? Let's make this as a meter bigger.
Wouldn't you know G, just whatever, like whatever material you do it, you know G?
Yeah, we know G and everything. We know G and everything.
You have to use that equation.
But if I use that equation, I haven't found the gap. The deformation is not given. You see? So let's say somebody give me the dimension of his specimen and everything, material property, G and everything. The question, how can I find tau max? Well, if you want to use this relation here, then you have to know the gamma, right? In addition to G. And if you know both of them, yes, you can put it here at particular radius, then you can find tau max. But I only know G, I don't know the gamma. So what should I do? I want to get this. Any idea? What did we do in bending? In bending, we said the stress, the bending stress, is equal to sigma max times y, measured with respect to the centroid. And then what did we do in order to get sigma max?
Diagrams.
Huh?
NC
MC over I. Yeah, but this comes from the fact that you already find sigma max. What did you do in order to? Yeah, you're getting close. Yeah. So exactly in the bending, that's the reason I say you have to read the derivation. If you don't read the derivation, you have to, mathematical proof. Of course, you're an engineer, you don't need to know that. But you have to do it at least once to understand how this relation is obtained. Why? Because when you want to apply them, you have to know their limitation. An assumption they are dry. If you don't know the limitation, you don't know where to apply them. So, what should I do in order to get this tau max? Exactly similar to what I did in order to get sigma max in bending. I said, let's use the law of equilibrium. Right? If I'm applying a torsion here, bending moment, sorry, a torsion moment, and this object, is it going to accelerate? No, it's in equilibrium, right? So what can I write? I can say that, if I cut it anywhere here, I can say that the sum of the moment coming from this element with respect to the centroid is what? You see this element, you have a shear load here, tau, at R. But I have it here. And this shear stress causes the shear load with respect to the centroid. So you have a kind of shear moment, right? The sum of this shear moment is what? Is equal to? Yeah, which is equal to? Which is equal to? No. Look, here I'm applying a bending moment T, right? So this T causes distribution of shear at all the elements, and each shear causes a shear force, and each shear force has a shear moment with respect to the centroid. So the sum of the shear moment is equal to what in order for this object to be in equilibrium? Huh? It's right here. It's right here, right? Bending moment. That means that what's the moment come from this element here? What's the moment come from that element? Is equal to tau at R times dA. What is that? This is a shear force. This is shear stress times dA, shear force. Right? Times moment R. What's the moment R? R. That's a particular small shear moment come from this element. But I have gazillion number of this element. So sum of all of them should be equal to what? The applied net torque. Otherwise, the object is not in equilibrium. It's going to accelerate. Right? So, this equation, hopefully, if I apply this equation, then I'll be able to find tau max. Now, let's go ahead and apply it. Integral over area tau of r is equal to tau max times radius over r. I'm just substituting this relation into tau. You see that? Times r right here times dA is equal to t. So what can I say? I can say take this out. This is a constant. Take it out. So you get right r max times divided by radius times integral r squared dA is equal to t. Now my question is, what is this going on here? No, it's not sensory.
Inertia.
It's inertia. It's polar motor inertia. If you go back to vector standings, we had Ixx, Iyy, and then I with respect to z, which was the radius time. So we call this polar moment of inertia. Polar moment of inertia. And we used to show it with J. Symbol that we use is J. So, what can I say about my tau max? Tau max is equal to, then we can solve this equation. You see, tau max times J over R is equal to T. You see that? So you can solve for tau max. So what do I get for tau max? Let's write here. Tau max is equal to TR over J. T times R over J is tau max. Now you can put it right here. Finally, you can find the distribution of shear stress. That's the goal, to find the distribution of shear stress. That's back to this relation. You remember I said we have the relation, but I don't have tau max. So it's completely useless. Now it's not useless because I do have the tau max. So I substitute here in this equation and I get, now replace it back. So I substitute this tau max here and then I get tau at radius r is equal to PR over J times R over R. This R cancel out and therefore you get TR over J. So let's put it here. The shear at any radius R is equal to T over J times R. Now if I give this relation to you, what is the maximum of shear? Well, this is just a linear function. The maximum happens when R is maximum. And where is R maximum? R, capital R. T, capital R times J. Isn't this exactly the same? And also this also satisfies this. In fact, this comes from here. So this is the end result that I'm going to use. So example. So in order to find that, what do you need to have? The applied moment. Well, how do you get the applied torsion moment? How do you get the applied torsion moment? At this section, let's say you have a, for example, this one. This part. Apply torsion. How do you get applied torsion at different sections? Well, you draw some sort of diagram. Right? We have axial load diagram, axial load, bending moment. Now you can draw a torsion moment diagram. I mean, it's the same. It's the same thing that we had before. All you have is direction is different. Right? So you get that. What else do you need? The distance from the centroid and oral moment of inertia. All of them you can compute. Therefore, you can evaluate that. Now, example. And the question is find axis stress. Find the maximum stress. What should I do? The first thing you ask, what kind of loading do I have here? It's perfectly torsion. And what was torsion? Shear. So you're going to develop some sort of force in every cross-section cause. You have some sort of polarly distributed shear forces that the value is obtained using this relation. So where is the maximum happening here? Well, R is equal to 2 centimeters. Right? So I'll just use this. You go to the appendix. You don't memorize anything. You just go to the appendix and say, well, this relation R is given. The torque divided by J times R. And when he's talking about maximum stress, I should put sub max here. That means R is equal to capital R. So this guy means it's equal to 2 centimeters, the outer radius. So I also have torque. The torque is equal uniformly everywhere. It's 2 kilonewtons per meter. So if I draw the torque diagram, right? Let's say this is positive. This direction is positive. You see? It's positive. So the torque, if I call it at any section here, so I have the bending moment this way, and then at this location it should be this way. In order to be able to the equilibrium. So this Q here and M at the X. If you take this at X from there, right? If you call it the bending moment, let's call it T. M is for, let's use capital M for bending moment. So let's use torque. Torque at any X from the left. If you take it this way, then you have positive TX dimensional moment, about this axis should be 0, right? So summation of moment, what is axis x, equals 0. That means T of x, negative 2k is equal to 0. That means the torque at any x point is equal to 2 kilonewton meter. That means that the torque here is not depending on x. It's not variable, right? It's not depending on x. That means I have this, and what is the value of that? 2 kilonewton meter. 2 times 10 to 3. I have R 2 times 10 to negative 2. What about J? I need to find J. So how can I find J? J is equal to the moment of inertia. We assume that this is completely solid, subtracted by this hole at the center. What's the moment of inertia of the solid one? Again, you do not memorize anything. You go to the appendix and you see there is a formula J is equal to pi over 2 R to the 4th power. And then you say, what should I write for the solid one? Pi over 2. What should I put for R for the solid one? 2. Oh wait. No, look, I want to use SI, metric system. So,
2 times 10.
that will greatly change the result. So you have 2 times 10 to negative 2. That's related to the 4th power. Am I done? Is that all? What should I do?
Pi over 2 or pi over 4?
Pi over 4 is the ixx pi over y. The polar one is, in the vector itself, there is a theorem that you didn't prove it. I is z or polar is summation of ixx plus pi over y. So pi over 4 plus pi over 4 is pi over 2. Alright? So, what should I add to that or subtract to that? Minus pi over 2, 1.5, 10 to negative 2 to the 4th power. So you get J from here, you have radius, you have torque, and then you do it right here. So you get 1x is equal to P, which is 2 times 10 to 3 times R, 2 times 2 divided by pi over 2, 2 times 10 to negative 2, 4 minus 1.5, 10 to negative 2, 4, do it in the calculator. So this, what I get here, what's the unit of that when I do the calculator? The end result. So what would be the unit of this? No, think about it. Pascal. The unit of that should be Pascal. So let's put in a calculator. I get is 2, 3, 2, 3, MPa. $233 megapascal. So 233 megapascal. What's the deviation that the max happens? This may be a question in the exam. Just explain the location of point inside parentheses S. Point or points. It may be 1 point, it may be many points. So what is the location of point that this maximum happens? It's in fact the location of the surface. All the points in the outer radius. It's not the one particular location. It can be. Sometimes we have problem that the location is only 1 point or one line, like one circle right here. Right? Just a particular circle. But here, because the shear is uniform, because the torsion is uniform, same everywhere, that maximum happens everywhere across the surface in the outer surface. Now what's the minimum? The minimum shear stress. I may ask, find the minimum. Well, do I have anything in the center? It's empty. So where is the location of minimum stress? So in order to evaluate it, what do you put? What's the modification to that equation? Tau mean. If I say tau mean, then what should I modify here? Well, the polar moment of inertia is pretty much the same, right? And according to this equation, tau is the same. I didn't have tau variation versus radius, then you say it's 1 tau here. Tau is the same. So this is also the same. Here, the only modification you have to evaluate that instead of 2, 1.5. Now, if you want to just quickly compute it, what do? You multiply, because this is only change. You multiply that by 1.5 divided by 2 to get rid of that 2. So your tau mean is equal to 283 times 1.5 divided by 2. 174 or 5 megapascal. So that's your max, that's your min. Now, I want you, if you have extra time at home, sometimes you play with this 3D modeling software, SolidWorks, ANSYS, you know. This time, go and create this object here. So what do? You go to the modeler, you draw this circle, you draw this circle, you subtract, and then you extrude it. Right? So you get this part. And you have all the dimensions. And then apply the torque. And then say run simulation. Then what you see, it creates a color contour, and then in the color bar, your maximum is equal to, these are red, and this is blue, minimum. Your red is equal to 233, 175, minimum. But are you going to exactly get 233? Is it going to be higher or lower? What happens near the wall? Look, this theory that we consider is only valid in the middle, that you are far from singularity. What happens near the wall? A stress concentration. You remember when we put that expression in the tension test, what was the point of failure? Near the area change. Right? That was the stress was maximum in group specimen. So here, the stress is way higher than what we compute from the formula. So if you do this in ANSYS, because it computes using finite elements, then your maximum is like 250. And that happens, the red is right here, stress concentration. But here, if you only consider this section, right, you're going to have this threshold and say, give me only this section. Just forget about this. Then you go exactly to 33, 175. But you can see that, what is the cost of doing it? The cost of doing that is to turn on your computer, run ANSYS, and go to the modeler, create that model, and create the mesh, create the boundary conditions, and then run the simulation, and then you see the result. It's very costly. What's the cost of what we did on paper? Just 2 floating point operations. That's the purpose of, when you get design equation like that, the purpose of design equation is for the engineer to rapidly come up with some conceptual design. Right? If you want to use computer to do that, you have to go through a lot of expensive cycles. So now let's compute the deformation, and then hopefully, I don't think we have time for the final review today, but we'll see. Now if I give a beam like here, if I say here you have 2K, and here you have here this way 2K, that means in 3D you have 2K, and then the other way 2K. And then I ask find the maximum shear stress or torsional stress. What do? First you have to draw some sort of diagram for the axial bending. See here, torsion, not bending. Here, this is related to tau over J over R. So you have to have T at any point. And that T is different. From here to here is 2. And then from here to here is going to be different. Right? Here from here is 0. From here to here is different too. Then you find the maximum of all sections before you put it in this formula. You have example in the next homework that I posted. You cannot just directly do these things. You have to first draw the diagram for these, the axial origin moment versus X, and see where is the location that maximum happens. Then pick the maximum, put it here, compute polar moment of inertia. Then you find the maximum distance from the center. And then you can find maximum. And if I say minimum, what do you do? Then you find the minimum. Right? So now we go to the angle of twist or torsional deformation. This is also very important. This is one of the important topics. So, this topic is deformation. Which is called angle of twist. So what was the deformation when we had pure axial load, either compression or tension? Well, we use sigma is equal to E epsilon. And sigma was F over A, E times delta over L. And this was my displacement, pure axial load and area. And then that was the deformed object, deformation. So this is for delta, and from here to here is L. Then I was able to compute delta according to FL over AU. We call this deformation, or actual deformation. Now, the question is, similar to that, if I go back to my physical intuition, I know that the moment I apply torsion or torque, what do I have? the specimen is going to twist a little bit, right? So it has deformation. According to the deformation means relative displacement. So it has deformation. Now the question is, what is that deformation? That deformation, unlike here, you see this was the strength, the normal strength, and it didn't have a unit, we mentioned this. Here, the deformation is just angle. What's the unit of angle? Meter? No. It doesn't, yeah, well, it's not physical unit. It's not meter, force, Pascal, it's nothing like that. So all I can directly do is the angle from my deformation. Right? And I know, according to what we showed earlier in this lecture, now is equal to G gamma. So angle of deformation, or just an object like that, which deformed like this, then I can relate the shear stress coming from this shear force, V over A, is equal to G gamma. I can relate the force to the angle of deformation. Now the question is, if I have the torsion, how can I relate the angle of deformation or angle of twist? You see here, deformation is not axial, it's purely twist. Now the question is, well, in the real life, do I have pure twist? No, I have axial load, I have bending moment. Now the question is, can I use all of them? This theories that I developed independently, can I put them in the same framework? How can I put them in the same framework? Superposition. So you can see now, you see we have a lot of question marks in this course. When we are studying this course, everything is just confusion. But eventually you get all this thing together and say, well, I have superposition. So instead of bringing a knowing bending moment and another axial load and considering a combined problem, I'll just focus on torsion separately. I develop some relation, then I'll focus on axial load. I develop some relation, then I'll focus on bending. Then I'll develop some relation, then I'll focus on pure shear. Right? And then using superposition, I can put them all together and integrate and compile our result together to get one real life problem. Right? So now that you know that, well, if I compute this angle, then I'm going to find something like delta and all it is to axial deformation. But again, you may ask this question. This is a more important question before we actually do that, before we complete this angle. Why do we do deformation analysis? Huh? A deformation. You see, if it's going to break or not, we only need maximum stress. We don't need deformation. Now the question is, why do we do yes?
It changes the amount of force on the other parts of the system.
Yes, but the purpose, what's the purpose of engineering problem solving? The purpose is to design. And when you design something, you want to know the forces on your system, right? And in this case, the purpose of doing deformation analysis is kind of ambiguous, because you say, well, I already found my tau max in both bending and shear. So I can estimate where is that maximum. So why do I need to do deformation? In fact, I asked the student before asking this question, which is a completely valid question. Now, I ask you, this is a meter layer. I ask you, say, well, let's not do deformation analysis like that. Forget about it. Then if I ask you to solve this problem, what are you going to do? Let's say you have a beam like that. Here. Okay. The question is, find reactions and the support. And do not use this relation, deformation. That's, you see, I'm trying to say the purpose of doing deformation analysis. But you may immediately say, well, I know the maximum, I know how to compute it, so I can design, because I know where the maximum, the failure happens. Well, I say yes, but in this problem, this is a completely practical problem. In fact, most of 99.99% of problem engineering are like that we are going to explain. You have many support reactions. Now the question is, find support reaction at point A and point B. How do you solve that? Can you solve it? And I said do not use deformation, because you said I already know my maximum and I can design. I don't need deformation. Then I say, well, this is a practical engineering problem. Solve it. Find the reaction at A and B. And then find the maximum stress, normal stress. How do you solve it? Can you solve it?
No.
Why?
No equations for two unknowns in one equation.
That's exactly right. So if you do system, this is system, right? And draw a FED, then you get, that's the system, and FED, then you get the force at A. I know I have nothing in the y direction, no bending moment, so I don't like it. And then net 2K here, 1K plus 1K, 2K. You see they don't generate moment, but it's symmetric. The same distance you have here, in the exam I may put this a little bit higher. So you have a kind of bending moment, right? And then what do you have here? FB. And then you may say, if you don't analysis, he did a good analysis. In fact, he is emailing me for improvement. The way he did one complete analysis. If you don't know how to do the analysis, say, oh, okay, that's perfect. I only have two on it. But look, how many equations do you have? You have one system in 2D, so you have three equations. But look, I've already got rid of the x and moment. So you only have one equation there. How many unknowns do you have? Can you solve it? Without using this? No. So you can't find FA and FB. As a result, you cannot find sigma, and as a result, you cannot find sigma max. And then you cannot design it, because you can't find sigma max. You cannot find force distribution. So you fail as an engineer. You fail. And let me tell you, what kind of problem is this? Indeterminate. Statically indeterminate. 99.99% of problem engineering is statically indeterminate. You never get something that you have a roller. You remember we had something like nice, good-looking roller here and a perfect pin, no friction. In fact, it's not roller. You always have some component of force in other direction. This is never a pin. You always have friction. So you always have more unknown than number of friction. Now, as a meter waiver, how can you actually solve that? Why? Now, this was statically indeterminate. That means if I only use vector static equations. Now, I bring the mechanics of material equations. How can you solve this system? By applying the deformation. That's the purpose of today's lecture, deformation analysis. Then, we need the number. Let's say this is from here to here is 1 meter. 1 meter. And now if you can solve that, that means from here to here, 1 meter, 1 meter. Then you get a meter waiver. Find FA and FP. And from here to here, diameter is equal to 2 centimeter. Diameter here is equal to 1 centimeter. Now you have a good motivation to do deformation analysis for torsion. The diameter is 2 centimeters from A to middle, and from middle to B is 1 centimeter, the diameter. You know what you can do, instead of using volume numbers, take these D from here to here. Take DA, DB, the diameter at A, diameter B, and LA. Instead of 1 meter, LA, LB. You see? Use parameters. LA, LB, DA, DB. So you don't need to do lots of calculation. Yeah. Before to work. And work is deformation. You get very close to that. Now you see, try to, what are we trying right now? We are trying to add one more equation because I already have one equation. Summation of 14x0. I'm trying to add another equation, so how many unknowns do I have? 2, FA and P. I'm trying to add one more equation, so I have 2 equations, 2 unknowns. So I'll be able to solve for FA. So here, if you have this, then this is not known yet, based on you writing. So we're trying to add one known equation. Well, that's extremely close there. Well, what do you see in that picture? Can you say anything about deformation at point in the middle? The deformation in the middle. I can't say anything about the middle point, midpoint, right? But I know that the deformation of two ends with respect to each other is 0. So the deformation of point B with respect to point A is equal to 0. That means in your equation, what's that deformation? End to end? When you wrote delta in your equation, what would be the value of delta? Which is deformation of B with respect to A? 0. Right? B with respect to A is 0. So if you use that, then that's going to give you one equation.
So this is the original vector statics equation.
Exactly.
Summation forces, and these are the two deflections. And since it's like it has no room to deflect, the deflection will be
It has
0.
no real room to deflect. So but you are missing something. Can you say that?
Is it this?
You are, everything is right. Right? This is completely acceptable. But when you want to find the F, you need to draw the axial load diagram. That means if you draw the axial load diagram, what's the axial load from here to here? If you cut it like that, you have the FA here, and then the axial load. And N plus FA is equal to 0, so N is negative FA. So from here to here, you need to have a negative sign. Right? So here what he said, you see the deformation. Thank you. And no, B is already positive because if you cut it here, You see B is this way, so you axial load this way is a tension. So B is positive, A is negative. So what he said, if you see, if I don't use vector, if I don't use the deformation, back to the main point, why are we studying deformation? That was the point. If you don't use the deformation, that means I don't use this. And that means I only use vector static equation. And I have two unknowns, one equation. I can never ever solve it. That means I cannot find maximum stress. That means I can never ever design it. So I'm completely failed. So now, if I have the option of deformation, which next class we're going to cover deformation for, force and also. This for only axial load. Now, if I have the option of deformation, then I can use this equation. But how can I use that equation? What I can say, if you apply load anywhere, this may deflect to the right as a result of this compression, tension. If you put it this way, then this is compression, tension. You see that? So I cannot say anything about the middle point. But I can say point B with respect to A is always at a constant distance. In his word, he said there is no room for this to go to the right. Right? That means the deformation delta B with respect to A is always 0. So what is the deformation of B with respect to A? Going back to the axial load analysis, the deformation of B with respect to middle plus deformation of middle with respect to A is equal to 0. What is the deformation of B with respect to middle? I use this relation. That means prior to do this analysis, you have to draw axial load diagram. So if I do that, you need to find the axial load from here to here, which is FB times LB divided by ABB using this equation, times E. Plus the deformation of middle with respect to A. FA does look negative. Here, if you call it here, this is FB, so axial load is tension, so you have positive here. Here, if you call it here, because I choose the sign FA this way, then the axial load will be this way, that is compression. So negative FA LA over A E is equal to 0. This is exactly this equation. This comes from the physics of deformation. Back to this topic. Now I have two equations, two unknown. When you go home, solve it numerically. When you solve it, you get something. You see, if you have perfectly symmetric 2K, then 1K is here, 1K here. Vector statics. Here, when you solve it, the result is non-intuitive. You cannot guess it. It doesn't have physics. Depending on how much area it's changing, you get different FA and FE. So this is the first example of non-indeterminate problem that we solved it numerically. Because how many equations do I have? How many unknowns do I have? Two equations, two unknowns. You can solve it. Independence. Right? So now you have some sort of motivation for the next class, because next class we're also going to have a final delivery immediately. Now let's do the torsion. Let's say now you have a bar here which is fixed between two walls. Okay? And then I apply a torque here. And this is point A, this is point B. Find the reaction and the supports. Can I solve it? How many unknowns do I have here? This T is what? T is 2K. What are those two? the reaction moment at A, the reaction moment at B. Two unknowns. How many equations do I have? This object is in 3 dimensions, but we have 6 equations. But look, in the x, y, z, I don't have any force. So I eliminate R summation of force in x, y, z. And in the x, I don't have moment, and in z, I don't have moment. I only have in the y direction moment. So how many equations do I have? Just one equation. How many unknowns do I have? So how can I solve it? The question as an engineer, they said, find the maximum stress and then design, find the diameter required to tolerate that stress. So how can I solve it? What do you observe? You see, in this case, when you apply a load like that, the deformation of B relative to A is 0. So how can I say about that?
Both of their twists is equal to 0. Equal to twist.
Right. Did you have this course before?
No, I had the torsion lab yesterday.
Yeah, this is the advantage of studying very well and not memorizing. The person that studies very well and not memorizing, always asking the question why, we get that equation. And what he said, look, this point is welded to the wall. You see the weld? So the angle of twist of this anything here on this surface is 0 with respect to the point here. So theta, the angle of twist of B with respect to A, is equal to 0. This is my second equation. So the first equation, summation of moment with respect to this axis 0, the second equation is that. So how many equations now do I have? How many unknowns? Then I can solve it. Right? Now in order to expand that, you need to have the relation between the angle of twist and torque that you are going to drive it next class. Then you can solve that from the problem.